2560 BC, the Giza Plateau. The sun rises over the western desert, casting long shadows across a landscape transformed by human ambition. A single limestone block, 2.5 tons of compressed ancient seabed, hangs suspended above the pyramid's growing summit. Below, hundreds of workers move in coordinated rhythm, their voices carrying commands across stone and sand. The block inches upward, defying gravity, defying logic. From this height, the Nile glimmers like a silver thread in the distance. Closer, the workers' village sprawls, temporary shelters for the thousands who have traveled here, not as slaves, but as citizens fulfilling sacred obligation. The copper tools they wield should be insufficient for this task. The wooden sledges should buckle, the ramps should collapse, yet the block rises. This is not the work of gods or aliens or lost technologies. This is human engineering at its most audacious, a civilization solving problems that wouldn't be attempted again for millennia. The question isn't whether they built the impossible. The evidence stands before us, enduring across 45 centuries. The question is how. The story begins not with pyramids, but with water. 3100 BC, the Nile River floods with seasonal precision, depositing rich black silt across its banks. Where other ancient peoples struggle against nature's chaos, the Egyptians find rhythm. The river dictates their calendar, their agriculture, their entire worldview. In this predictability, civilization takes root. King Narmer, later called Menes, unifies Upper and Lower Egypt, forging a single kingdom from disparate communities. The union creates something unprecedented, a centralized state with concentrated resources, organized labor, and a divine mandate. The pharaoh isn't merely a king. He is the living embodiment of Horus, the bridge between mortal and eternal, and gods require monuments. The early dynastic period begins modestly. Mud brick mastabas, flat-roofed rectangular tombs, house the noble dead. But ambition grows with each generation. By the third dynasty, around 2670 BCE, Pharaoh Djoser commissions his vizier Imhotep to design something revolutionary. At Saqqara, the step pyramid rises, 6 massive tiers of stone reaching 62 meters into the sky. It is Egypt's first major stone structure, a stairway for the pharaoh's soul to ascend to the heavens. Imhotep's innovation transforms everything, stone not mud brick, permanence not decay. The Egyptians possess the necessary materials in abundance. Limestone cliffs line both sides of the Nile Valley. White and golden Tura limestone lies across the river. Granite waits in Aswan's quarries, 600 miles to the south. The river itself becomes a highway, capable of transporting massive loads during the annual inundation when water levels rise and boats can navigate closer to building sites. But materials alone don't build pyramids. The Old Kingdom pharaohs, beginning with the 4th dynasty around 2613 BC, and a sophisticated bureaucratic state, provincial governors called nomarchs oversee regional resources. Scribes track inventory with meticulous hieratic script on papyrus scrolls. Priests maintain the religious calendar that determines construction seasons. This administrative apparatus can mobilize tens of thousands of workers, coordinate food distribution, manufacture tools, and sustain multi-decade projects. The workforce itself reveals Egypt's social structure. Modern archaeological evidence from worker villages, particularly at Giza and Amarnash, utters centuries of misconception. These aren't slaves dragged in chains. The laborers are Egyptian citizens performing corvée duty, a rotational labor tax owed to the state. Farmers arrive during the inundation season when fields lie underwater and agricultural work halts. They work 3 or 4-month shifts before returning home. They receive payment in food, bread, beer, meat, vegetables, and medical care. Their tombs found near the pyramids bear inscriptions of pride, friends of Khufu, or drunkards of Menkora. The religious dimension cannot be overstated. To the ancient Egyptians, death is transformation, not ending. The pharaoh's successful transition to the afterlife ensures cosmic order. Maat continues, the Nile will flood, the sun will rise, chaos will be held at bay. The pyramid isn't vanity, it's existential necessity. Every block placed is an act of devotion, every ramp constructed a prayer in stone. By 2560 BC, when Khufu ascends the throne, pyramid construction has become Egypt's defining achievement. His father Sneferu built 3 pyramids, the bent pyramid, the red pyramid, and the collapsed pyramid at Meidum. Experimenting with angles and internal structures, perfecting techniques through trial and catastrophic error. Khufu inherits this accumulated knowledge, along with a kingdom at its economic and organizational peak. He orders a pyramid that will dwarf all predecessors. The Great Pyramid will consume approximately 3 million stone blocks, averaging 5 tons each, with some granite beams in the king's chamber weighing up to 80 tons. The base will cover 13 acres with sides oriented to cardinal directions with accuracy within 1/15 of a degree. The original height of 146.5 meters will make it the world's tallest human-made structure for 800 years. The logistics are staggering. Tura limestone quarries across the Nile provide the smooth outer casing. Aswan granite for internal chambers requires 600-mile Nile transport. Copper tools need constant replacement. One estimate suggests tens of thousands of copper chisels consumed during construction. Food provisions for the workforce demand agricultural surplus from across the kingdom. Wooden sledges, ropes, and rollers require timber imports from Lebanon, since Egypt's native trees are too small for heavy engineering. Yet Khufu's architects, whose names are lost, though later tradition remembers Himiunu, the king's vizier, possess something more valuable than materials. They have geometry, astronomy, and mathematical principles sophisticated enough to calculate volumes, predict structural loads, and maintain precise measurements across massive scales. They understand leverage, friction, and incremental progress. They think in decades, not days. The Great Pyramid's construction likely spans 20 to 25 years of Khufu's reign. At its peak, the project might employ 20,000 to 30,000 workers, a figure suggested by Greek historian Herodotus 20 centuries later, but now partially confirmed by archaeological evidence of the worker settlement size at Giza. The organization required to house, feed, and coordinate this population represents administrative achievement, as impressive as the engineering itself. This context unified state, religious imperative, accumulated knowledge, sophisticated bureaucracy, and willing workforce creates the conditions for the impossible to become inevitable. The journey from Djoser's step pyramid to Khufu's geometric perfection is measured in failures as much as triumphs. Sneferu's reign, 2613 to 2589 BCE, becomes a vast laboratory of architectural experimentation. At Meidum, his first pyramid begins as a step structure before being converted to a true pyramid with smooth sides. The outer casing collapses, possibly during construction, leaving a 3-stepped tower emerging from a debris field. The lesson is harsh but educational. The angle matters. Undeterred, Sneferu commissions the bent pyramid at Djoser. Construction begins at a 54-degree angle, steep and ambitious. Halfway up, the builders recognize the danger. The weight and angle create unsustainable internal pressures. Rather than abandon the project, they adjust mid-construction, reducing the angle to 43 degrees. The result is distinctive, bent, and stable. The pyramid stands as physical evidence of ancient engineers learning, adapting, solving problems in real time. The Red Pyramid, Sneferu's third attempt, applies these lessons. A gentler 43-degree angle from base to apex. Massive blocks laid in horizontal courses, internal chambers designed with corbelled ceilings to distribute weight. It succeeds. Egypt's first true smooth-sided pyramid, rising 105 meters. When Sneferu dies, he leaves his son Khufu not just a kingdom, but a perfected methodology. The Fourth Dynasty 2006, 113 to 2004, 194 BC represents the Pyramid Age's apex. Khufu, Khafre, and Menkaure build the Giza complex, each pyramid slightly smaller than its predecessor, but the overall achievement unmistakable. The Sphinx, carved from living bedrock, guards the plateau. Causeways connect valley temples to mortuary temples. Subsidiary pyramids house queens and royal family. Boat pits hold disassembled cedar vessels, ceremonial barks for the pharaoh's solar journey. But the scale proves unsustainable. The Fifth Dynasty pyramids Userkaf, Sahure, Neferukara are smaller, built with inferior materials, employing rubble cores rather than solid limestone. Many have collapsed into unrecognizable mounds. The Sixth Dynasty continues this decline. By the end of the Old Kingdom around 2181 BC, pyramid construction effectively ceases. The centralized power that made such projects possible fractures during the First Intermediate period. Regional governors assert independence. The administrative apparatus that mobilized tens of thousands crumbles. Yet Egyptian engineering ambition doesn't die, it transforms. 1550 BC, the new kingdom emerges from the chaos of the Second Intermediate period, reunified under Theban pharaohs. The capital shifts south to Thebes, modern Luxor. The focus shifts from pyramids to temples, from tombs visible on the horizon to hidden sepulchres carved into valley cliffs. The Valley of the Kings becomes the royal necropolis, designed to thwart tomb robbers through secrecy rather than mass. But if the pyramids represented vertical ambition, the new kingdom temples embody horizontal grandeur. Karnak Temple Complex, dedicated to Amun-Ra, grows across 2,000 years of continuous construction. The Great Hypostyle Hall, built primarily under Seti I and Ramesses Roman II around 1290 to 1224 BC, contains 134 columns arranged in 16 rows. The central columns rise 21 meters, their capitals wide enough for 50 people to stand upon. Each column consists of multiple stones weighing several tons, precisely fitted without mortar. The ceiling stones span column to column, creating a forest of stone that still inspires awe. The engineering challenge shifts from lifting blocks vertically to positioning them at tremendous heights while maintaining structural integrity. The columns aren't solid, they're hollow with rubble fill, reducing weight without sacrificing strength. The foundations dig deep into Nile sediment, distributing loads across broader bases. The mathematics of column spacing, load, bearing capacity, and lateral stability represent sophisticated understanding of structural engineering. Ramesses Roman II, who reigns 1279 to 1213 BC, becomes the new kingdom's greatest builder. At Abu Simbel, his engineers carve an entire temple facade from a solid cliff face. 4 colossal seated statues of Ramesses, each 20 meters tall, flank the entrance. The temple extends 63 meters into the mountain. Twice yearly, on February 22 and October 22, the rising sun penetrates the entire length of the temple, illuminating statues of Ramesses and the gods in the inner sanctuary. Astronomical precision applied to architecture. The Ramesseum, Ramesses Roman II's mortuary temple on the Theban west bank, once housed a granite statue of the pharaoh weighing approximately 1,000 tons, among the largest monolithic statues ever transported and erected. Though now toppled and broken, its fragments testify to engineering capabilities that rival pyramid construction. Obelisks present another category of impossible achievement. These single-piece granite pillars, quarried in Aswan and transported hundreds of miles down river, stand before temple entrances as symbols of solar worship. The Lateran obelisk, now in Rome, weighs 455 tons and originally stood 32 meters tall. Hatshepsut's obelisk at Karnak, erected around 1457 BC, weighs 343 tons. Quarrying, transporting, and erecting these monoliths without cracking them requires techniques we're still reconstructing. Archaeological evidence from the 20th and 21st centuries revolutionizes our understanding of how these projects were accomplished. In 1990, Egyptologist Mark Lehner and stonemason Roger Hopkins attempt to quarry, transport, and raise a small obelisk using reconstructed ancient techniques. They succeed, but barely, confirming that the methods are plausible but extraordinarily difficult, requiring extensive experience and coordination. Worker village excavations at Giza by Lehner and Zahi Hawass reveal brewery facilities, bakeries, copper workshops, and medical facilities. Fish bones and cattle remains indicate workers received protein-rich diets. Healed fractures in skeletal remains show medical intervention. Graffiti on pyramid blocks names work gangs, Friends of Khufu, vigorous gang. These aren't oppressed slaves, they're organized labor forces with identities and pride. The 2013 discovery of papyrus fragments at Wadi al-Jarf, a Red Sea port, provides unprecedented documentary evidence. Written by Mur, an inspector during Khufu's reign, the papyri describe daily logistics of transporting Tura limestone from quarries to Giza. The text mentions specific officials, delivery schedules, and administrative procedures. It's the oldest papyrus ever discovered and confirms the bureaucratic sophistication underlying pyramid construction. Tool discoveries add technical detail. Copper chisels, worn to stubs from use, litter quarry sites. Dolerite pounders, extremely hard stone balls used to hammer granite, show distinctive wear patterns. Wooden sledge fragments from tomb contexts match sledge depictions in tomb paintings. Even ancient rope, preserved in dry desert conditions, reveals braiding techniques capable of bearing multi-it unloads. The picture that emerges isn't mysterious, it's methodical. The ancient Egyptians didn't possess lost technologies or alien assistance. They possessed something more powerful: accumulated knowledge, patient experimentation, massive organizational capacity, and sheer determined ingenuity applied across generations. By the time Ramesses III builds his mortuary temple at Medinet Habu around 1150 BC, Egyptian civilization has been constructing monumental stone architecture for 1500 years. The techniques are refined, the traditions deep, the institutional memory vast. What seems impossible to modern observers would have seemed merely difficult to ancient engineers who inherited centuries of collective problem-solving. The question isn't whether they could build these structures. The evidence proves they did. The real question, the one that pulls us deeper into investigation, is which specific techniques, among many plausible methods, they actually employed, and how they coordinated human effort on scales that still challenge modern project management. Angle 1. The human factor the workers who built the pyramids wake before dawn. In the settlement southeast of the Giza Plateau, thousands of temporary residents stir in long barracks-style buildings. The smell of baking bread fills the air. Industrial scale bakeries produce enough loaves to feed 20,000 people daily. Fish arrives from Nile Delta fisheries. Cattle, slaughtered in designated areas, provide protein reserves unimaginable for common Egyptian farmers. This is no slave camp. Archaeological evidence from the workers' village reveals a community, not a prison. The settlement includes copper workshops where tools are manufactured and repaired, medical facilities where bone setters treat construction injuries, and even a small brewery. Skeletal remains show healed fractures, tibias broken and properly set, vertebrae damaged and treated. In an era when most ancient laborers worked until their bodies failed, these workers received medical care. The organization follows military precision. Workers divide into competing gangs, a Friends of Khufu and Victorious gang, their names daubed in red ochre on stone blocks. This isn't merely identification, it's pride. Modern graffiti from construction workers follows similar patterns. Crews leave signatures, claim their work, compete informally over who accomplished more challenging tasks. The rotation system prevents permanent displacement. Farmers arrive during Akit, the inundation season from July to November when fields flood and agricultural work halts. They fulfill their back obligation, a labor tax owed to the state, working 3 to 4 month shifts before returning to their villages. During construction's peak, 20 to 30,000 workers might occupy Giza simultaneously, but they're constantly cycling through, replaced by fresh crews. Motivation transcends mere obligation. The pyramid ensures cosmic order. The Pharaohs' successful ascension to the afterlife maintains the fundamental balance that keeps the sun rising, the Nile flooding, and chaos at bay. Every worker participates in this divine project. The tomb inscriptions found near the pyramids don't express resentment. They express honor. "I labored on the pyramid" becomes an epitaph worthy of remembrance. The administrative apparatus supporting this workforce rivals the engineering achievement itself. Scribes track grain deliveries, tool distribution, and worker attendance on papyrus scrolls. Overseers coordinate between quarries, river transport, and construction sites. Officials manage housing, food distribution, and conflict resolution. The project operates like a vast machine, each component synchronized with precision that modern project managers would recognize and respect. Angle 2, mathematical precision. The Great Pyramid's base covers 1 acres 230, 4 meters per side. The accuracy is staggering. The 4 sides deviate from perfect squareness by less than 2 inches. The sides align to cardinal directions: north, south, east, west, with error margins within 1/15 of a degree. This isn't approximate. This is intentional, calculated precision implemented across a massive scale. The ancient Egyptians achieved this through astronomy and geometry, not modern instruments. They observe circumpolar stars, stars that never set below the horizon, tracking their rotation around the celestial North Pole. By marking 2 positions of a star and bisecting the angle, they establish true north. The technique requires patient observation and geometric understanding, but it works with accuracy that rivals modern surveying. The slope angle 51.84 degrees derives from mathematical relationships. The pyramid's height divided by half its base width equals approximately 1/27, close to the golden ratio phi, though likely coincidental. More deliberately, the pyramid's proportions reflect the Egyptian understanding of the seekt, their measurement system for slopes. 1 seekt equals the horizontal distance per cubit of vertical rise. The Great Pyramid uses a seekt of 5, a ratio that produces stable, aesthetically pleasing proportions. Leveling the base presents another mathematical challenge. The foundation deviates from perfect level by only 2.1 centimeters across the entire 230-meter width. The Egyptians accomplished this through water level, in cutting trenches around the perimeter, filling them with water, and marking the waterline. Water naturally finds its level. Once marked, they cut the bedrock to this reference plane, creating a foundation of extraordinary flatness. Volume calculations determine material requirements. The pyramid contains approximately 3 million blocks. Assuming 23-year construction, based on Khufu's probable reign length, requires placing approximately 270 blocks daily, or 1 block every 2 minutes during a 10-hour workday. These calculations inform workforce size, material quarrying rates, and transport logistics. The ancient architects must perform similar mathematics, planning years in advance to ensure stone supply meets construction pace. The internal chamber design demonstrates sophisticated geometric thinking. The king's chamber measures 46 by 5, 23 by 5, 82 meters, a precise 2:1 length to width ratio. The grand gallery ascends at 26.5 degrees, matching the descending passage angle exactly. The corbelled ceiling, each course of stone projecting slightly inward until the gap closes, distributes weight away from the chamber, preventing collapse. This isn't trial and error, it's calculated structural engineering. Surveying techniques maintain accuracy across the enormous worksite. The Egyptians use merkhit, a plumb-line tool resembling a simple transit, along with bay palm ribs as sighting instruments. By establishing a baseline and using triangulation, they transfer measurements across hundreds of meters while maintaining precision. Each block's placement must align with this overall geometric plan, requiring constant measurement and adjustment. Angle 3. Stone quarrying and transport. The limestone quarries at Giza still bear evidence of ancient extraction methods. Trenches cut 3 sides of rectangular blocks, leaving one side attached to bedrock. Workers use copper chisels, softer than stone but effective when copper is abundant and disposable. Pounding them with wooden mallets, the copper dulls quickly. A single block might consume dozens of chisels. But Egypt's eastern desert copper mines provide sufficient supply, and workers recycle dull tools constantly. For harder stone, the technique shifts. At Aswan's granite quarries, dolerite pounders, extremely hard igneous stone balls become the primary tool. Workers grip these 8 to 12-pound spheres and pound granite repeatedly, pulverizing the surface grain by grain. The process is tedious, exhausting, and effective. Experimental archaeology confirms one worker can remove approximately 5 inches of granite weekly using this method. The unfinished obelisk at Aswan, abandoned in the quarry when a crack appears, shows these pounding grooves across its entire surface. The final separation from bedrock employs wooden wedges. Workers cut narrow channels beneath blocks, insert dried wooden wedges, then soak them with water. The wood expands with tremendous force, several tons of pressure per wedge. The block cracks free along predetermined lines. This technique leaves characteristic wedge marks visible in quarries and on certain pyramid blocks. Transport from quarry to construction site presents the next challenge. For Giza's local limestone, the distance is short, hundreds of meters. For Tura limestone from across the Nile, distances reach 10 kilometers. For Aswan granite, the journey extends 600 miles upriver. The sledge becomes ancient Egypt's primary heavy transport technology. Wooden sledges, low platforms with upward, curving runners, attached to stone blocks with ropes. Teams of workers pull these sledges across prepared surfaces. A famous Middle Kingdom tomb painting at Jehutep's tomb shows 172 men hauling a colossal statue on a sledge. One worker stands on the statue's base, pouring liquid, probably water, onto the sand ahead of the sledge. This detail isn't decorative, it's technical documentation. In 2014, physicists at the University of Amsterdam conducted experiments proving that wetting sand reduces friction by up to 50%. The water creates capillary bridges between sand grains, increasing stiffness and preventing the sledge from sinking. The amount of water matters. Too little provides no benefit, too much creates mud. Ancient Egyptians discovered the optimal ratio through experience. Roller systems, long hypothesized, show less archaeological evidence. Wood doesn't preserve well in most conditions, and no definitively identified rollers have been found at pyramid sites. However, wooden fragments that could be roller sections exist in museum collections. The debate continues, though sledges appear more commonly documented in Egyptian art and texts. River transport solves the long-distance challenge. During the Nile's inundation, water levels rise several meters, allowing boats to navigate closer to construction sites via temporarily navigable canals. Barges, flat-bottomed boats designed for heavy cargo, transport multi-ton blocks. The Wadi al-Jawf papyri specifically mention Murrah's team transporting Tura limestone by boat, making multiple trips between Quarry and Giza. The engineering extends to harbor facilities. At Wadi al-Jawf on the Red Sea coast, archaeologists discovered an elaborate harbor with galleries carved into hillsides for boat storage, along with anchor systems for securing large vessels. Similar infrastructure likely existed at Giza, though later construction has obliterated most evidence. Ramps, internal, external, spiral, or combination systems, remain archaeology's most debated topic. No ramp survives intact at any pyramid site, but ramp fragments and building debris suggest their existence. The external straight ramp theory requires a ramp as voluminous as the pyramid itself by the time the apex is reached. Plausible. Spiral ramps circling the pyramid make more sense volumetrically, but complicate corner accuracy. Internal ramps, revealed through microgravity scanning at the Great Pyramid, might have existed within the structure itself, though this remains controversial. What's certain, the Egyptians moved millions of tons of stone across significant distances using wood, rope, copper, human muscle, and profound understanding of physics, friction, leverage, incremental progress. They didn't defy physics, they mastered it within technological constraints that make their achievement more impressive, not less. Angle 4, lifting technologies, the fundamental challenge of pyramid construction, reduces to a simple problem, moving mass vertically against gravity. A 2.5-ton limestone block must rise from ground level to heights exceeding 140 meters. The ancient Egyptians possessed no pulleys, no wheels for heavy transport, no internal combustion engines. What they have is leverage, inclined planes, and human coordination. The ramp remains the most plausible primary lifting mechanism, though its exact configuration generates intense scholarly debate. French architect Jean-Pierre Houdin proposes an internal ramp theory, a spiral corridor built within the pyramid's outer shell, allowing blocks to be hauled upward through the structure itself. Microgravity and thermographic scanning conducted in 2017 revealed anomalies in the Great Pyramid's internal structure consistent with such corridors, though conclusive proof remains elusive. External ramps present different challenges. A single straight ramp reaching the pyramid's apex would need to extend over a mile to maintain a functional gradient, approximately 7 to 10 degrees for teams of men hauling sledges. Such a ramp would contain more material than the pyramid itself. The logistics become absurd. More likely, the Egyptians employed multiple ramp configurations at different construction stages. During initial construction phases, simple straight ramps suffice. The pyramid base is broad, heights are modest, and ramp gradients remain manageable. As the structure rises, the system adapts. Zigzag ramps along one face, switchback ramps on corners, or spiral ramps circling the structure all appear in various scholarly models. Archaeological evidence from the Red Pyramid shows remnants of an external ramp system. though erosion and later stone quarrying have destroyed most details. Lever technology supplements ramps for fine positioning and final adjustments. The shaduf, a weighted lever arm used for lifting water in irrigation, demonstrates Egyptian familiarity with leverage principles. Applied to stone blocks, teams of workers using wooden beams as levers can lift one edge of a block, insert packing stones beneath it, then repeat the process on the opposite edge. Incrementally, the block rises. Experimental archaeology proves 3 or 4 workers can raise a height, unblock several meters through patient lever work. The French stonemason and engineer Jean-Philippe Lauer, who spent decades studying Egyptian construction, successfully demonstrated lever lifting techniques at Saqqara. His teams raised blocks using only wooden poles, rope, and coordinated effort. The process is slow, hours per meter of vertical gain, but it works. Combined with ramps bringing blocks near their final positions, lever systems handle the precise final placement. Counterweight systems might have assisted with specific challenges. Cut channels at some pyramid sites could have accommodated counterweight mechanisms. Heavy stones attached to ropes running over simple beam fulcrums, providing mechanical advantage. While no definitive counterweight apparatus survives, the principle is simple enough that Egyptian engineers could have independently developed it. The Great Pyramid's internal design reveals another lifting strategy, the corbelled ceiling in chambers and galleries. Rather than lifting massive capstone beams to span wide chambers, the builders use corbelling. Each course of stone projects slightly inward until the gap closes. This technique appears in Neolithic tombs worldwide, but Egyptian architects refine it to monumental scale. The Grand Gallery's corbelled ceiling rises 6 meters, demonstrating mastery of this weight distribution method. For the truly massive stones, the granite beams in the King's Chamber weighing up to 80 tons, the lifting challenge becomes extreme. These monoliths likely required specialized cradles, larger teams, and possibly sand-based lifting platforms. One theory proposes encasing the chamber in sand, placing the beams on top, then excavating the sand to lower the beams into position. Evidence for this technique is circumstantial, but the logic is sound. Sand provides infinitely adjustable support and controlled descent. What becomes clear through archaeological experimentation is that no single technique explains all lifting challenges. The Egyptians employed adaptive strategies, different methods for different situations, refined through generations of accumulated knowledge. The impossible becomes possible through patient, incremental engineering. Angle 5. Temple engineering. Temple construction presents challenges distinct from pyramids. Where pyramids emphasize vertical mass, temples demand horizontal grandeur. Vast halls filled with forests of columns, each column a height, an assembly of precisely fitted drumstones. Karnak's Great Hypostyle Hall epitomizes this achievement. Constructed primarily under Seti I and completed by Ramesses II around 1250 BC, the hall measures 103 meters by 52 meters, roughly the size of a modern football field. Within this space stand 134 columns arranged in 16 rows. The 12 central columns tower 21 meters tall with capitals 3.5 meters in diameter. The remaining 122 columns reach 13 meters. The ceiling stones spanning between columns weigh several tons each. The engineering challenge multiplies across every element. Each column consists of multiple cylindrical drum stones stacked vertically. These drums must align perfectly. Any misalignment compounds as the column rises, leading to structural instability. The Egyptians achieve alignment through central wooden poles run through holes cut in each drum's center, keeping the stack vertical as it grows. Once complete and secured with mortar, the wooden pole is removed or left to decay. Foundation engineering beneath these columns is equally sophisticated. Karnak sits on Nile sediment, not bedrock. To prevent settling and collapse, the builders excavate deep foundation pits, fill them with compacted sand and rubble, then lay massive stone foundation blocks. These foundations distribute the column's weight across broader areas, preventing the compression and differential settling that would topple the structure. The ceiling stones, massive beams spanning from column to column, require precise lifting and positioning at 13 to 21-meter heights. Ramps built around the growing temple allow teams to haul these beams into position. As columns rise, the ramps rise with them, creating a constantly evolving construction landscape. Once the ceiling is complete, the ramps are dismantled, revealing the finished hall. Abu Simbel represents a different engineering paradigm, carving architecture from living rock. Around 1264 BCE, Ramesses Roman II orders a temple carved into a sandstone cliff in Nubia, 600 miles south of Thebes. The facade features 4 seated colossi of Ramesses, each 20 meters tall, carved directly from the cliff face. The temple extends 63 meters into the mountain, terminating in a sanctuary containing statues of Ramesses and 3 gods. The astronomical alignment is extraordinary. Twice yearly, February 22 and October 22, the rising sun's rays penetrate the entire temple length, illuminating the sanctuary statues. The dates likely correspond to Ramesses' birthday and coronation anniversary, though some scholars debate this interpretation. Regardless, achieving this alignment requires precise orientation calculations, accounting for latitude, solar declination, and the temple's internal geometry. The carving process proceeds from top to bottom. Workers begin at the cliff's summit, cutting downward as they define the colossi's features, heads first, then bodies, then thrones. This sequence prevents debris from damaging completed lower sections. The removed stone is hauled away continuously, preventing accumulation that would impede work. Inside, chambers are carved following similar principles, ceiling to floor, back to front. Obelisk erection presents perhaps the most dramatic engineering spectacle. These single-piece granite pillars, some exceeding 30 meters tall and 400 tons, must be transported from Aswan quarries, shipped hundreds of miles by river, then raised vertically without cracking. The Lateran obelisk, originally erected by Thutmose Roman III and Roman IV at Karnak around 1450 BC, weighs 455 tons and stands 2 meters tall. Moving this monolith requires a specially constructed barge, likely wider and more robust than standard Nile vessels. The Wadi al-Jarf papyri mention boat construction for heavy transport, suggesting the Egyptians built custom vessels for specific projects. Erecting the obelisk employs a controlled tipping method. Workers dig a ramp leading to a prepared stone base with a curved lower edge. The obelisk, lying horizontally, is hauled up the ramp with its base positioned over the mounting base. As the tip extends beyond the ramp's end, controlled ropes and sand-filled pits allow gradual rotation. As the obelisk tips toward vertical, sand is released from the pit in controlled amounts, slowly lowering the base onto its mounting point. The entire process requires hundreds of workers operating in precise coordination. The unfinished obelisk still in Aswan's quarry, intended to reach 42 meters and weigh approximately 200 tons, demonstrates the method's limits. A crack appeared during quarrying, rendering it unusable. It remains attached to bedrock, its pounding marks visible, a testament to ambition that exceeded even Egyptian engineering capacity. These temple achievements, golem forests, cliff temples, towering obelisks, prove Egyptian engineering wasn't limited to pyramid construction. The principles transfer, patient material removal, incremental progress, sophisticated geometry, and massive coordinated labor applied to diverse architectural challenges. Angle 6. Tool innovation. Egyptian engineering advances in lockstep with metallurgical development. The tools available at any given period define what structures are possible. During the early dynastic period and Old Kingdom, the Pyramid Age, copper is the primary metal. Egyptian copper comes from Sinai Peninsula mines and eastern desert deposits. The metal is relatively soft, unsuitable for modern construction, but adequate when treated as a consumable resource rather than a durable tool. Copper chisels are manufactured in vast quantities. Archaeological evidence from pyramid worker villages reveals copper workshops with crucibles, molds, and slag heaps. Workers pour molten copper into open stone molds, creating rough chisel blanks that are then hammered to shape and sharpened. A chisel might cut limestone effectively for a few hours before dulling beyond usefulness. The spent chisels return to the workshops for remelting and recasting. This consumption rate seems wasteful by modern standards, but it's economically rational within Egyptian context. Copper is relatively abundant, while trained stonemasons are scarce. Better to consume cheap material than slow construction, waiting for tools to be sharpened. Estimates suggest tens of thousands of copper chisels were consumed during the Great Pyramid's construction, a staggering number that reflects both the project's scale and the tool's limitations. For harder stones, granite, basalt, diorite, copper proves insufficient. The Egyptians turned to dolerite, an extremely hard igneous rock found in the eastern desert. Dolerite pounders are shaped into spheres or elongated hammers weighing 8 to 15 pounds. Workers grip these stones and pound granite surfaces repeatedly. The technique is brutally simple and effective. Granite's crystalline structure fractures under repeated impact, pulverizing grain by grain. Experimental archaeology by Denise Stocks, an Egyptologist specializing in ancient technology, demonstrated that one worker using dolerite pounders can remove approximately 5 cubic inches of granite weekly. This seems slow until scaled to teams of workers operating simultaneously across multiple surfaces. Aswan's unfinished obelisk shows pounding marks across its entire 42-meter length, evidence of hundreds or thousands of workers hammering in coordinated rhythm. Sawing represents another tool innovation. Egyptian saws are copper blades, sometimes exceeding 2 meters in length, used with sand or emery abrasive. The saw itself doesn't cut, the abrasive grit does. Workers pour quartz sand mixed with water into the saw kerf, then draw the copper blade back and forth. The sand, caught between copper and stone, grinds through granite with surprising efficiency. The saw marks preserved on sarcophagi and stone blocks show characteristic parallel grooves left by the abrasive action. Tubular drills employ similar principles. Hollow copper tubes, 6 to 30 centimeters in diameter, rotate with abrasive sand, cutting cylindrical cores from stone. The Petrie Museum in London holds granite cores extracted by such drills, their surfaces marked with spiral grooves. These cores prove the technique's effectiveness, though debates continue about rotation mechanisms. Bow drills for small holes, steam-powered rotation for larger cores. Bronze introduction during the Middle Kingdom around 2000 BC provides marginally harder tools. Bronze is copper alloyed with tin, producing a metal harder and more durable than pure copper. However, the improvement is incremental, not revolutionary. Bronze tools last longer, but don't fundamentally change construction techniques. The massive temple projects of the New Kingdom still rely on patient abrasion, pounding, and leverage. Iron arrives late in Egyptian history. Widespread use only begins around 600 BC, well after the Pyramid Age and major temple construction periods. The engineering achievements that define ancient Egypt occur in the Copper Age and Bronze Age, making them more impressive, not less. Tool marks preserved on unfinished works provide direct evidence of techniques. The quarry marks at Aswan, the saw cuts on unfinished sarcophagi, the chisel marks on pyramid backing stones, these aren't mysteries. Their documentation, modern stonemasons examining these marks recognize the patterns. The spacing indicates copper blade width, the groove depth reveals pressure applied, the scratch patterns show abrasive grain size. The innovation isn't the tools themselves. Copper chisels and stone hammers are ancient technologies appearing in multiple civilizations. The innovation is scale, manufacturing tools in sufficient quantities, organizing workers to use them effectively, and sustaining these operations across decades. The tools are simple. The logistics are extraordinary. 2560 BC, the 23rd year of Khufu's reign. The pyramid stands nearly complete, its white Tura limestone casing gleaming across the Giza plateau like an artificial mountain born of human will. Only the summit remains unfinished, a flat platform measuring approximately 3 meters square, awaiting the final piece that will transform construction site into monument, the Pyramidion. This capstone, carved from a single block of granite or possibly covered in electrum, a gold, silver alloy that would catch sunlight visible for miles, represents more than architectural completion. It is the Benben, the primordial mound that emerged from the waters of chaos at creation's dawn. Placing it transforms the structure from stone pile into sacred geometry, from building into cosmic instrument. The logistics of this final placement represent the culmination of 23 years of accumulated engineering knowledge. The Pyramidion weighs several tons. Estimates range from 2 to 6 tons depending on its exact dimensions and material. It must be hauled to the pyramid's summit at 146 meters elevation, positioned precisely on the center of the platform and secured. Any error, any dropped load would scar the casing stones below and mar the achievement. The ramp system, whatever configuration has served throughout construction, reaches its terminal point. Workers haul the Pyramidion on its wooden sledge, ropes straining, men chanting rhythmic work songs to synchronize effort. The air at this height feels different. Wind whips across the exposed summit. The Nile Valley spreads below like a map drawn by gods, and every worker present understands they are participating in history. Lever teams position themselves around the platform edges. As the sledge arrives, they begin the careful process of final adjustment. Wooden beams slip beneath the Pyramidion's edges. Teams lift in coordinated pulses, calling back and forth, while other workers slide packing stones beneath the rising corners. Inch by inch, the capstone rises above its sledge, suspended on a forest of wooden levers and human muscle. Surveyors, the priests and scribes who have maintained geometric precision throughout construction, check alignment. The Pyramidion must center exactly over the pyramid's apex, its 4 triangular faces aligned with the 4 casing stone faces below. Any rotation, any offset, would be visible to observers on the ground and would constitute failure in a project defined by perfection. The adjustment process takes hours, perhaps days. Slight shifts left, then right, then forward. The surveyors sight along the edges using their Merc-hit tools, calculating angles against the sun's position and the cardinal directions they established years ago when the foundation was laid. Everything must align, not approximately, but exactly. The religious dimension intensifies the moment's weight. Priests burn incense, the smoke rising from censers as prayers in Khepri, the morning sun god, and Ra, the eternal sun. The pyramid is a machine for resurrection, a geometric spell that will enable Khufu's Ka, his life force, to ascend to the heavens when death eventually comes. The Pyramidion is this machine's final component, the point from which the Pharaoh's spirit will launch skyward. The foreman's signal, the lever team's coordinate one final lift. The Pyramidion rises clear of its packing stones. Below, workers remove the supports. Slowly, with infinite care, the levers lower. The pyramidion descends toward its prepared seat. Stone touches stone. The workers hold tension on the levers, ready to adjust if the fit proves imperfect. It settles. The surveyors rush forward with measuring cords and plumb lines. They check every angle, every edge, every alignment. The pyramidion sits centered within tolerances measured in fractions of inches. The geometric perfection that defines the entire structure extends to its apex. The impossible has been achieved. A roar erupts from the workers, not just those on the summit, but the thousands below who have watched the final placement. The sound carries across the plateau, across the temporary village, across the Nile to quarries where more workers prepare stone for future projects. The Great Pyramid is complete, but completion requires more than placing the capstone. The interior chambers, the king's chamber, the queen's chamber, the grand gallery, must be sealed according to sacred protocol. These spaces will house Khufu's sarcophagus, his funerary equipment, his provisions for the afterlife. They cannot remain accessible. Deep within the pyramid, final preparations proceed. The king's chamber 10, 46 by 5, 23 by 5, 82 meters, its walls precision, cut granite, receives the red granite sarcophagus carved to hold Khufu's mummified body. The sarcophagus is slightly wider than the ascending passages, proving it was installed during construction, not after. It sits precisely aligned with the chamber's geometry, its placement calculated years ago. Above the king's chamber, the 5 relieving chambers, bases designed to distribute the pyramid's weight away from the burial chamber, stand empty except for quarry marks and builders' graffiti. One mark reads "Friends of Khufu," a work gang's signature on stones that would remain hidden for 4,000 years. These workers knew their names would be sealed in darkness, yet they signed their work anyway, claiming their role in eternity. The sealing process begins with the Grand Gallery, this soaring corbelled passageway 6 meters high, 46 meters long, ascending at 26 degrees, serves a final mechanical function. 3 massive granite blocks, each weighing several tons, rest on wooden restraints at the gallery's base. These blocks will slide down the ascending passage when released, plugging it permanently. Workers position themselves throughout the gallery, ready to execute a choreographed withdrawal. The plan requires precision: release the blocks, exit through the descending shaft system, and seal the entrance. All before the blocks wedge the passages closed. There is no rehearsal. The timing must be perfect. The priests complete their final rituals. Offerings are placed: food, beer, incense, protective amulets. Prayers are spoken, their words echoing off granite walls that will hold these sounds for the last time before centuries of silence. The sacred texts are recited, ensuring Khufu's journey through the Jewat, the underworld, will follow prescribed paths toward resurrection. The signal comes. Workers pull the restraining wedges. The granite blocks lurch, then slide, accelerating down the ascending passage with ominous grinding echoes. Workers scramble down the descending passages, their oil lamps flickering, their footsteps urgent. Behind them, stone meets stone with thunderous finality. The plugging blocks wedge into position, sealing the ascending passage. Additional blocking stones are hauled into place from below, filling the descending passage. Smaller stones, mortar, rubble, all packed tight, creating a barrier designed to deter tomb robbers for eternity. The workers seal themselves out, climbing through the original entrance passage and emerging onto the pyramid's north face. Outside, teams prepare the final casing stone for the entrance, a pivoting stone designed to blend seamlessly with the surrounding casing, concealing the pyramid's entry point. The stone swings into position. Masons apply mortar to the joints, chip away identifying marks, polish the surface until it matches the surrounding stones. The entrance vanishes, the Great Pyramid stands complete and sealed. Its 3 million blocks rest in geometric precision. Its internal chambers hold their secrets. Its casing stones reflect sunlight like a beacon visible for miles across the Nile Valley and the surrounding desert. The structure that seemed impossible when conceived 23 years ago now dominates the horizon, undeniable proof of human capability pushed to its absolute limit. Khufu himself, now in his 40s or 50s, his reign spanning more than 2 decades, gazes upon the completed monument. Every resource of the Egyptian state has focused toward this achievement. Thousands have labored. Copper chisels have worn away by the tens of thousands. Rope has frayed and been replaced. Sledges have broken. Workers have been injured, some killed in accidents. Yet the pyramid stands, a mountain of human determination made tangible. This is the moment when the impossible becomes real, when engineering theory becomes physical fact, when generations of accumulated knowledge prove sufficient to the greatest challenge ancient Egypt has yet conceived. 1264 BC, Nubia, 600 miles south of Thebes. The desert heat shimmers across sandstone cliffs on the western bank of the Nile. Ramesses II, now in the 6th year of his reign, still young but already ambitious beyond measure, stands before a cliff face that will become his southern statement of power. This is not pyramid construction. This is something different. Architecture carved from living rock, a temple that doesn't sit on the landscape but emerges from within it. Abu Simbel represents engineering's transformation. Where Khufu built upward, Ramesses II builds inward. Where old kingdom architects assembled millions of blocks, New Kingdom engineers remove thousands of tons of stone to create empty spaces that serve the same purpose, glorifying the pharaoh, ensuring cosmic order, projecting immortality. The facade design is audacious. 4 seated colossi of Ramesses, each 20 meters tall, will flank the temple entrance. They will not be assembled from blocks like the Ramesseum statues. They will be carved directly from the cliff face, the mountain itself transformed into royal portraiture. The technical challenge differs entirely from pyramid building, but demands equivalent precision. The work begins at the cliff's summit. Teams of stonemasons establish the colossi's crowns, the double crown of Upper and Lower Egypt, carved in 3-dimensional relief 60 meters above the desert floor. This top-down approach is deliberate. Debris from upper sections won't damage lower, already finished work. The removed stone, thousands of tons of sandstone, is hauled away continuously using ramps that descend from the working face. The carving proceeds with mathematical precision. The face of each colossus must be identical, recognizably Ramesses, carved on a scale that makes facial features visible from hundreds of meters distant. The sculptors work from small models and detailed drawings, scaling up proportions using grid systems. A finger on the model translates to a finger 1 meter wide on the cliff face. Every measurement must multiply correctly. Any error compounds across the massive scale. The sandstone itself presents both advantages and challenges. Softer than limestone or granite, it cuts more easily with copper and bronze tools. But it's also more fragile, prone to fracturing if struck improperly, vulnerable to flaking along bedding planes. The masons must rid the stone constantly, adjusting technique to the rock's natural structure, working with the grain rather than against it. By 1260 BC, the facade nears completion. The 4 colossi sit in eternal stillness, their hands resting on their knees, their gazes fixed eastward across the Nile toward the rising sun. Between their legs, smaller figures, royal family members, protective deities, emerge from the rock in deep relief. Above the entrance, a niche holds a statue of Ra-Horakhti, the sun god, carved to receive the dawn's first light. Inside, the engineering challenge shifts to astronomical precision. The temple extends 63 meters into the mountain, terminating in a sanctuary containing 4 seated statues: Ra-Horakhti, Amun-Ra, Ta, and Ramesses Roman, 2 deified, the pharaoh taking his place among the gods. The entire structure must be oriented so that twice yearly, on specific dates, sunlight penetrates the full depth and illuminates these statues. The dates, February 22 and October 22 by the modern Gregorian calendar, likely correspond to Ramesses' birthday and coronation anniversary, though Egyptian calendars were lunar and would drift against solar years. Regardless of the exact symbolic meaning, achieving this alignment requires calculations accounting for latitude, solar declination, the angle of the rising sun, and the temple's precise orientation. The architects established the alignment through astronomical observation and geometric calculation. They track the sun's rising position across multiple days, marking azimuths on the horizon. They calculate the temple's bearing to intersect with sunrise on the target dates. The corridor is carved following this precise heading. Any deviation of even a degree would cause the light to miss the sanctuary or arrive on wrong dates. On February 22, 1259 BC, the first solar alignment after temple completion, priests and officials gather in the Preed, on darkness within the sanctuary. The temple dedication has brought nobles from Thebes, tributary chiefs from Nubia, and priesthoods from temples across the kingdom. This moment will prove whether the engineering calculations were correct. The eastern horizon brightens. The sun's disk emerges above distant hills. Its first rays strike the facade, illuminating the colossus' faces with golden light. The beam shoots through the entrance, racing down the hypostyle hall, through the vestibule, penetrating into the sanctuary's darkness. The light touches Ra-Horakhti's face. It spreads across Amun-Ra's features. It illuminates Ramesses' deified countenance. Only Ta, god of craftsmen and the underworld, remains in shadow, appropriate for a deity associated with darkness. The alignment is perfect. The impossible calculation, executed in stone across 63 meters of carved mountain, succeeds. The priests erupt in praise. The assembled officials witness divine favor made manifest. Ramesses himself, present for this inaugural alignment, sees his architect's promises fulfilled. The temple is not merely architecture. It's a cosmic machine, synchronized with the heavens, proving that Egyptian engineering can bend both stone and sunlight to the pharaoh's will. But Abu Simbel represents only one achievement in Ramesses' Roman II's unprecedented building campaign. At Thebes, his mortuary temple, the Ramesseum, pushes the limits of statue engineering. 1255 BC, Western Thebes, the Ramesseum rises across 13 acres of Nile floodplain, its pylons, courtyards, and hypostyle halls following New Kingdom temple conventions. But in the second courtyard stands something exceptional. A seated colossus of Ramesses carved from single granite block, approximately 17 meters tall when complete, weighing an estimated 1,000 tons. Moving this monolith from Aswan quarries required engineering at maximum scale. A specialized barge, probably over 60 meters long, reinforced with extra timbers, was constructed specifically for this transport. The loading process at Aswan involved controlled flooding of a dock basin, floating the barge beneath the statue, then allowing water levels to drop, settling the stone's weight onto the vessel. The Nile journey, 600 miles and several weeks, tested every component of the barge's structure. The weight distribution had to prevent capsizing. The current required constant management. Stops for repairs and adjustments likely occurred multiple times. When the barge finally reached Thebes, the unloading process reversed the loading sequence. Flood a dock basin, float the barge in, raise the statue using ramps and levers as water recedes beneath it. Erecting the colossus demanded a massive ramp system and hundreds of workers. Ropes attached to the statue's back allowed teams to pull, while other workers used levers to lift the base incrementally. The process likely took weeks. Patient, careful raising of the center of gravity until the statue balanced over its base, then final lowering into position. The result dominated the Ramesseum's courtyard, a granite mountain of royal propaganda. Inscriptions on the statue's shoulder proclaimed Ramesses' titulary: King of Upper and Lower Egypt, strong and right is Ra, chosen of Ra, son of Ra, Ramesses, beloved of Ammon. The statue wasn't merely art. It was theology in stone, royal power made physically overwhelming. At Karnak, Ramesses adds to the great hypostyle hall, begun by his father, Seti I. The completion of the hall's decoration, tens of thousands of square meters of relief, carving covering every column, wall, and ceiling block, represents a different engineering triumph, organizing hundreds of sculptors and painters to create visually coherent narratives across vast surfaces. The scaffolding required to reach the upper sections of 21-meter columns must support multiple workers simultaneously, along with their tools and paint supplies. The platforms must be stable enough for precise chisel work. The decorative program must be coordinated so that relief styles match across surfaces carved by different hands. The logistics rival construction itself. By 1250 BC, Ramesses' building projects span from Nubia to the Delta. His name appears on more monuments than any other pharaoh. Some of these are new constructions, others are older structures that Ramesses appropriates, carving his cartouches over previous rulers' names. Are architectural theft on a grand scale, but also proof of engineering confidence. Ramesses knows his architects can modify, expand, and improve whatever earlier pharaohs built. The engineering peak isn't merely about individual monuments. It's about systemic capability, the administrative apparatus that can conceive, plan, and execute multiple massive projects simultaneously across a kingdom stretching 1,000 miles. It's about training sufficient craftsmen, securing adequate resources, maintaining quality standards, and sustaining effort across decades. Ramesses Roman II reigns for 67 years, among the longest reigns in Egyptian history. When he dies in 1213 BCE, he leaves a landscape transformed. His temples dominate Thebes, Nubia, and the Delta. His statues, dozens of colossi, proclaim his presence across the kingdom. His obelisks stand at multiple temple entrances, their inscriptions praising his achievements. This is the climax not just of individual projects, but of Egyptian engineering itself. The techniques refined over 1,500 years, from Djoser's step pyramid through the 4th dynasty pyramids, through Middle Kingdom refinements, to New Kingdom temple complexes, reach their fullest expression. The civilization has mastered stone on every scale, from jewelry to obelisks, from amulets to temples carved from mountains. The engineering isn't static tradition, it's living practice, constantly adapting to new challenges. Abu Simbel's astronomical alignment demonstrates new applications of ancient geometry. The Ramesseum's colossi push transport and lifting techniques to their limits. The hypostyle hall's completion shows organizational capacity managing vast decorative programs. This is mastery, not merely the ability to repeat previous achievements, but the confidence to attempt what hasn't been done before and the expertise to succeed. The impossible has become routine, the extraordinary has become expected. Egyptian engineering stands at its zenith, a civilization that has learned to shape reality itself according to its vision of cosmic order and divine kingship. The monuments stand as proof the calculations work. The stones rise, settle, and endure. The engineering works not because of lost secrets or external intervention, but because generation after generation of Egyptian architects workers, and administrators have refined their craft until they can accomplish what appears miraculous to those who don't understand the patient accumulation of knowledge, the disciplined application of mathematics, and the coordinated effort of thousands working toward shared purpose. This is the turning point, not the moment when Egyptian engineering emerges, but when it reaches its maximum expression, demonstrating capabilities that won't be matched until civilizations with fundamentally different technologies arise millennia later. The monuments stand, but the civilization that built them begins to change. 2181 BC, the sixth dynasty collapses into chaos. Regional governors assert independence. The centralized authority that mobilized pyramid building workforces fragments. The first intermediate period begins, a century of political division, economic disruption, and cultural anxiety. The Pyramid Age effectively ends. Later pharaohs attempt to continue the tradition. The 12th dynasty, 1991 to 1008, 102 BC, sees renewed pyramid construction under Amenemhat I, Senusret I, and their successors. But these Middle Kingdom pyramids employ different techniques and betray resource constraints. Where Old Kingdom pyramids used solid limestone cores, Middle Kingdom pyramids substitute mud brick cores faced with limestone casing. The engineering knowledge persists, but the economic capacity to execute at Old Kingdom scale has vanished. The results are visible today. Most Middle Kingdom pyramids have collapsed into shapeless mounds. Without solid stone cores, they couldn't withstand millennia of environmental stress. The limestone casing stones, valuable building material, were quarried away by later generations. What remains barely resembles pyramids at all. Only archaeological investigation reveals their original form. The contrast with Old Kingdom pyramids is stark. Khufu's pyramid, Khafre's pyramid, even the Red Pyramid, all maintain recognizable geometry 45 centuries later. The casing stones are mostly gone, stripped away during medieval Cairo's expansion when builders needed ready, cut limestone. But the massive core blocks remain, too large and numerous to be efficiently quarried. The structures endure through sheer mass and solid construction. The engineering lesson is clear. Techniques matter, but so do materials and resources. Middle Kingdom architects understood pyramid geometry and construction methods. What they lacked was the centralized power and economic surplus to implement at Old Kingdom scale. Engineering knowledge can persist even when political capacity to apply it declines. The New Kingdom 1550 BC onward abandons pyramid construction entirely. The reason is practical. Pyramids advertise tomb locations. Despite sealing, despite plugging blocks, despite hidden passages, nearly every pyramid was robbed in antiquity. Tomb robbers, motivated by gold and precious materials, defeated every architectural defense. They tunneled around plugging blocks, they excavated through fill, they persisted until they reached burial chambers. The New Kingdom pharaohs choose a different strategy: secrecy. The Valley of the Kings, a remote desert wadi west of Thebes, becomes the royal necropolis. Tombs are cut deep into cliff faces, their entrances concealed after burial. No monumental superstructure advertises location. The theory, what can't be found can't be robbed, the theory fails. Nearly every Valley of the King's tomb is robbed in antiquity, many within decades of sealing. Only Tutankhamun's tomb, accidentally buried under debris from later tomb excavations, escapes major looting. When Howard Carter opens it in 1922, he finds that even this hidden tomb was entered twice in antiquity, though robbers were apparently interrupted before removing significant contents. Yet the engineering tradition doesn't vanish, it redirects. The monumental impulse that built pyramids now builds temples. Karnak, Luxor, Abu Simbel, the Ramesseum, Medinet Habu. These structures received the resources, labor, and architectural ambition that once went to pyramids. The construction techniques evolve, but the underlying engineering principles persist: precise geometry, massive stone assembly, coordinated labor, administrative organization. Temple construction continues through the late period 664 to 332 BC, though at reduced scale. The Ptolemaic dynasty, ruling after Alexander's conquest, builds temples at Edfu, Dendera, and Phila, following traditional Egyptian architectural forms despite being ethnic.